Okay, so welcome back to sampling and experimental design. Today we're going to pick up where we left off with the interaction model. So let's do a quick recap, and then I want to show you some examples of what we mean by interaction, and then we're going to move on to doing hypothesis tests for interaction. So first, let's just do a quick recap. So here is the completely randomized model, okay, with T treatments. Where the T treatments are, we're focusing specifically on the case where the T treatments are a combination of two factors. Okay, so T equals, so you have factor A with T sub A levels and factor B with T sub B levels, and these are the factor combinations that give us the T treatments. Okay, and so these are treatments, and we are looking at them specifically to ask whether these two factors combination of factors A and B and we're specifically writing out the model with interaction parameters. Interaction. Okay, so this is the model. It looks like, so we can write this way. So y sub ijk is equal to the overall mean plus an effect of the ith level of factor A and the effect of level j of factor B, and then interaction parameters for the ith level of A and jth level of B, and remaining residual variability are sub ijk, which are normally distributed error terms. Okay, so this is simply another way of representing the CRD model with T treatments. Okay, so recall this is simply a different way of writing the CRD model. And that's an important thing to remember because that tells us how many free parameters there are. Okay, so let's pick it up from here, and I want to explicitly write down now the free parameters associated with each of these blocks of parameters, with alpha, lambda, and gamma, and these correspond to the different treatment means that are possible when there are T treatments. Okay, so let's illustrate this point by asking this question. So how many free interaction parameters? Okay, so interaction parameters are these gammas. So let's be clear. So we're talking about the gamma ij terms. Okay, so let's work this out in a couple of steps. So first, let's remember that this is just another way of representing the completely randomized design with T treatments. And so in that model, we know that the treatment effects were parameterized instead using tau 1 up to tau t. Okay, so there were t minus 1 free parameters. For the treatment effect parameters, so for the tau i's. Okay, so remember there are t taus in that model, so this is just another way of writing that model. There are t taus, and there's one constraint. The taus have to sum to 0, so that mu represents the overall mean. Okay, so therefore there is one constraint, so t minus 1 free parameters. Okay, in CRD model with T treatments. Okay, so because this is simply another way of writing that model, we know that this must equal, so t minus 1 must equal the total free parameters among these three sets of parameters that we're now using to replace the tiles. Okay, so it must equal the number of free parameters among the ones we've used here in this model. So among the alphas, the lambdas, and gamma. Okay, so that must be true. Okay, so alpha and lambda are somewhat easier to count, so let's do that first. So we know that the alphas need to sum to 0, so it has t sub a, the number of levels, one less than that because of the constraint. Summation alpha must equal 0, and so this is the number of degrees of freedom is the free parameters in the main. Remember, we call the alpha is the main effect, so that's the average effect of the different levels of factor A if we hold everything else fixed. Okay, so there are t a minus 1 free parameters in the alphas. Okay, and then likewise there are t sub b minus 1 free parameters in the lambdas. Okay, that govern the main effects of factor B. And so therefore, if we subtract, then we know that we can now count how many free parameters there are among the interactions. Okay, so let's just do that math here. So let's do t minus 1. Okay, and let's subtract these the free parameters for the alphas and the lambdas. So let's subtract off t sub a minus 1, and also subtract off t sub b minus 1. Okay, so let's work out what this is. And what is t? T, when there's two factors, can simply be represented as ta times tb, all the possible combinations of the two factors. So I'm going to replace that. Okay, so I'm going to rewrite that as ta times tb. Okay, we simplify everything. There's minus ta and there's minus tb. And then we have minus 1, plus 1, and then plus 1. So we have plus 1 at the end. Okay, and so this actually looks a little bit familiar like an expression that we've also seen in randomized block design. In other words, we can factor this. We can factor this expression. Okay, so this factors nicely into t sub a minus 1 times t sub b minus 1. Okay, so therefore this quantity must be the number of parameters must equal the number of free interaction parameters. Parameters. Okay, so here it's worth making this this extra point here is notice is so the number of interactions. This tells us how many interaction terms there are. Okay, so now think of this special case. Imagine there's only 2 levels of A and 2 levels of B. Okay, so if there's only 2 levels of A and B, then TA is 2, TB is 2, and so you notice this just becomes 2 minus 1 times 2 minus 1. So in other words, there's only one interaction possible when there are only 2 levels each of the for each factor. So in other words, this is the case where there are 4 treatments, which is equal to 2 times 2. Now, the reason I want to draw that to your attention, bring that to your attention, is because we've seen a case where there were 4 treatments, a combination of 2 of one factor and 2 levels of another factor. Okay, and this was the example where we looked at seeing how long you would stay awake using 2 possible drinks, coffee and tea, and 2 possible donuts. Okay, chocolate donut and maple donuts. Okay, so even though we can't give you coffee and donut, you can certainly emote coffee and tea in chat to help yourselves stay awake. Okay, so so why is that significant? Well, there are 4 treatments, and there's actually only one possible interaction according to the math we just did when there are when it's a two-factor 2x2 experiment. So when we looked at that drink and donut example, we looked at a number of contrasts. Okay, so we could see how. Okay, so actually, so now that I talked about this, it would be helpful to write that out briefly so you can see what's going on. Okay, so in that case, there were only 4 treatments. So 1, 2, 3, 4, and so you had drink, which was coffee, tea, and donut, which was chocolate, maple, chocolate, and maple. Okay, and so at that point we had treatment effects. Okay, so in that model we had tau 1, tau 2, tau 3, and tau 4. And what I'm saying is that in this special case where there's 4 treatments, it's a combination of two levels of 2 factors. In fact, there's only one interaction, and one of the contrasts that we wrote down, in fact, is the interaction. So let me just write it out, and then hopefully you see the connection. Okay, so interaction means that whether the effect of coffee is different or not, depending on which donut you ate. Okay, so we said that the model is additive if there is no interaction. Okay, so what's the contrast here that actually is another way of testing for that interaction? Okay, so you look here. So if you look at the difference between 1 and 3, well, that's holding chocolate fixed and changing the drink from coffee to tea. And if you look at the difference between 2 and 4, that is again holding the donut the same and then changing the drink. Okay, so therefore the interaction here, there's only one possible interaction. That's exactly what I've just described. So only one possible interaction here. Okay, and it's exactly as I described. So there's no interaction. So the null hypothesis would be asking whether the difference between coffee and tea is the same for either donut. Okay, so that's going to be tau 1 minus tau 3. Okay, so this would be the null hypothesis. Okay, tau 1 minus tau 3. Okay, so whether the difference between coffee and tea is the same for either donut, tau 2 minus tau 4. Okay, so this is in fact simply the interaction in this special case of 2 factors, each with 2 levels. Okay, so this is this interaction. So in words, so you see it again. So this is the in words. This hypothesis asks whether the effect of the drink is the same for either donut. Okay, so that's how the interactions and contrasts are related in this special case. Okay, so that asks. Oh, I'm sorry. I need to null hypothesis whether these differences are the same. So null hypothesis that they're 0. Okay, so in this case, there's only one possible interaction, and it can be written as a contrast. So this can actually the interaction can actually be done as a test of contrast. So test of contrast means it is a t-test where you use the coefficients on the treatment effects to carry out the test of hypothesis. Now, the reason we're doing this more general interaction model is to help us take care of the case where there are more than 2 levels for each factor, in which case it is no longer just a single interaction effect. We would be asking whether any of the interactions are equal to are significant. Okay, so we're asking whether there are multiple such interactions, and we're asking whether all of them are 0. And so therefore, when you move from 2 2 levels each to more than 2 levels, then that's why we need to develop the corresponding ANOVA F test. Okay, so just to recap what I've been saying, when there's just 2 levels of each of the 2 factors, there's only one interaction, and it can be done either via a contrast t-test, which has this interpretation, or it can be done using an f-test. Now, when you have more than 2 levels, then the only way to test for all the interactions is to use an f-test. Okay, so that's where we're going with this. Okay, then I wanted to connect that with this example that we've looked at before. Okay, so now next up is of course estimation. So let's write down the parameter estimates. Okay, so there's a question in chat that asks, why is that the only interaction? What about the effect of donut is the same for either drink? Okay, so that's a great question. All you need to do is also write those. Okay, actually, I'll do it on the board here. So the way we wrote it was tau 1 minus tau 3. We're testing whether that is equal to tau 2 minus tau 4. If you do it the other way, so if you do donut first, so you fix the drink and then you do the donut, you'd be testing versus tau 1 minus tau 2 equals tau 3 minus tau 4. Okay, that's what I had up here on the table. And you notice, if you look at these two equations, this is actually the same. This is actually the same test. All we did was move tau 2 over here, okay, and we moved tau 3 onto the right hand side. Okay, so this is just actually 2 ways of expressing exactly the same interaction. So there's really just one unique interaction. So that's a great question. Thanks for asking that. And then this explains why there's only one unique interaction. Same interaction could be expressed in 2 different ways. Okay. Next is estimation. So we need to set up the least squares optimization, and from there we're going to get the estimates for all of these parameters. We need mu hat, alpha hat, etc. So we need hats for all of these parameters. So we need to do another constraint least squares optimization. Okay, so next is estimation. Okay, so now we need to do a minimization. Now we need to optimize all of these sets of parameters. So we optimize over mu, alpha, lambda, and gamma. Okay, and so the least squares expression that we're minimizing is to take the observations, so the data points, they're y, I, j, k, and then subtract what the model is fitting for them. So we're fitting all of this stuff as the model prediction. Okay, so we're going to estimate the alphas, the lambdas, and the gammas. Okay, so that's what we're minimizing. It's the least squares expression. And we're going to do that subject to all the possible constraints. Okay, there are many constraints on the parameters. Okay, I didn't write. We wrote some of them out last time, but suffice for now. This is a constraint minimization, and so this leads to the estimates. Okay, so mu hat. Okay, so the interpretation is more important than plugging through all the mathematical details here. Okay, so mu hat. So there's nothing. So this is the usual expression. Okay, we know this is just another way of writing the CRD. So mu hat, we learned, is simply the average of all the units. Okay, so now instead of using indexing the treatments with I, we're now using I and J for the two factors to index the treatments. So to take the average of everything, we're taking the average over all the levels of A, all the levels of B, and all the replicates. Okay, so therefore Y bar with three dots, we're averaging over all 3 subscripts. Okay, now the rest of the expressions actually follow quite intuitively. So first we need the estimates of the effects of the levels of A, so that's alpha I hat. Okay, so it's very intuitive because we simply, to get the effect of level I of factor A, all we have to do is average everyone who was assigned that level. So average over all the assignments on factor B and all the replicates. So essentially everyone who is assigned level I of factor A, okay? So the difference from that and the overall mean gives us the effect of factor A level I. Okay, so alpha is the parameter for the treatment, the level effect of factor A. Okay, and so the lambda is also exactly the same form. So if you want to do this for level J of factor B, then you just average all the units assigned to level J of factor B. So it's y bar dot J dot. So everyone assigned to level J of factor B, and then take the difference from that to the overall mean. So there's a question that says, what is K? Okay, so the reason we have triple subscript here is we're using the first two subscripts to index which treatment we're getting. Okay, so we need to use both I and J to specify which treatment. So for example, I might be coffee and then J might be chocolate donut. Okay, so we need both subscripts to inform which treatment we're in, and so K is simply the index for the replicates. So K would go from 1 to R, or however many replicates are assigned to that treatment. Okay, so that's why we have an extra subscript, because we're explicitly writing down indices for the two factors separately. Okay, so that's so these are the estimates for the effects, and then finally we now need an estimate for the interaction parameter. Okay, so this one looks a little bit like the expression that we saw for randomized block design. So let me first write it down. So this is the estimate for gamma ij. Okay, so we do the average assigned to that treatment. So remember ij, the specific combination of ij refers to now a specific treatment. So y bar ij is actually the mean of that treatment. Okay, this treatment has level, let's say, coffee and chocolate donut. Okay, so this is the average of everyone assigned that treatment. Okay, so from there, so y bar ij, and then average everyone in that treatment. So we need a dot for the third subscript. So this is the average of everyone assigned to that particular treatment. Okay, and then we subtract off the average for level I. So that's related to the alpha term we had before. So y bar I, and then two dots, and then subtract the same thing but with factor B fixed. So that's with j dot, and then finally add back the overall mean. Okay, so that's the result that comes out of this least squares optimization. Okay, so those are the parameter estimates. Now, once you have the parameter estimates, you also get an estimate for the residual. So let me give myself a little more space here. Okay, so now we need the estimate of the residual variance term, that's sigma squared hat. Okay, so in general, we need to divide by the degrees of freedom. So what is the degrees of freedom that we need here? Okay, so remember this, again, it's very simple once we remember that this is just another way of writing the CRD. Okay, so in the completely randomized design, degrees of freedom would be T, the number of treatments, times 1 less than the replicates. Okay, so T times R minus 1. So here, treatment is simply represented as now the factors of A times the factors of B. So T, so you just have to change T to TA times TB, because that's just another way of representing the total number of treatments. Okay, and then we have 1 less the number of replicates, so R minus 1. Okay, so that's the degrees of freedom we need. And so once we have that, then we just need to do, in this case, a triple summation. So over the factors of the two levels and also the replicates. So I'm just going to condense it into a single summation. So this actually represents a sum over all the possible values for all of I, J, and K. Okay, and then we're summing over the residuals, which is the observed values, y, I, j, k, minus the fitted values, which means plugging in everything we estimated, mu, alpha, lambda, and gamma. Okay, so that's the observed value minus the fitted model fitted value. And so actually, if you plug in all of these estimates, we can simplify this a little bit. So this entire term actually simplifies to something quite so it really reduces quite nicely. So we end up with just y I, j, k minus the y bar I, j dot. Okay, now actually that should make a lot of intuitive sense, because what is y bar I, j dot? Well, that is simply the treatment mean associated with the factor I of A and J of B. Okay, so this is actually exactly the same residual, sum of squares residual as we saw in CRD. Okay, in CRD it was the treatment mean minus it was the treatment mean subtracted from the observation, and this is exactly the same thing here. We're taking each observation, subtract the corresponding treatment mean. Okay, then that's the residual. Okay, so that's why it's useful here to keep remembering that this is simply another way of writing the CRD. Okay, so therefore the expression for the residual exactly matches what we would expect under the CRD. Okay, so before I do hypothesis testing, I do want to show you some visual examples of interaction. So I'm going to switch to the slide here. Okay, so over here, I want to show you some illustrations of how interaction looks like. Okay, so let's start off with simply a two-factor, two-level example. Okay, so much like the drink and donuts. Okay, so how do we visualize interaction? So suppose, just to illustrate, we want to look at the effects of diet and exercise on weight loss. Okay, so let's just make two factors. So we tell our subjects to either diet or not diet, and exercise or not diet or not exercise. So therefore, there are 4 treatments. Okay, so we're going to measure the amount of weight they lost. Okay, so there's 4 treatments in total, and so of course we can do what we've done before and summarize the data by plotting the average for each treatment. Okay, so that's on this slide. So there are 4 treatments, so they're indexed as okay, so no diet, no exercise, diet but not exercise, and then finally on the right hand side, both diet and exercise. Okay, so this, so we've seen actually plots like this, except previously we'd probably do a box plot. Here, instead of a box plot, because we just plotted the average in each treatment, so that's why there's only a single point. So we're using just the single point. For example, 1 is the average of everyone assigned to go on a diet but not exercise. Okay, so we have these 4 treatment means. Okay, so remember, each of these points really represents everyone who was assigned to that treatment. So of course the downside of this sort of plot is you don't get a sense of how much variability there is. Okay, so there's no you don't see how large sigma squared would be just by looking at this plot. Okay, but this is helpful because it allows us to lay out how these responses are associated with treatment. Okay, so here I've laid it out like just 4 linearly on the x-axis, but instead of plotting them separately, we can use the same visual, just rearrange it slightly, and use it to examine whether there's interaction. Okay, so in this next plot, all I'm doing is taking the 4 points and just stacking them together in a different way. So on the x-axis is just the 2 levels for diet, so whether it's yes or no. Okay, so you notice these 4 points are simply the original 4 points, but mapped to have this display. So down here, so that's why there's two lines now stacked on top of each other. Okay, so no diet and no exercise is now this bottom left point. Diet without exercise is this one, and then for each of these, we can also do it with where exercise is yes, and so those are represented by the red points. On the left is no diet but exercise, and then both exercise and diet. Okay, so this is what we call an interaction plot, because this kind of plot allows us to see whether these 2 factors interact. Okay, so in this case, we would say that there is no interaction, and we would say that there is an additive effect of the 2 factors. Okay, so how do we tell? So if you look at this plot, so if you are not on a diet, then exercise helps you gain. So if you take the difference between, on the left-hand side, the red dot and the blue dot, this plot is saying that on average, if you don't diet, then exercise helps you helps you lose. I think that's how it was done. Helps you lose 2 pounds. Okay, so the net benefit is 2 pounds. And so if you go over here, the difference between the red dot and the blue dot is also 2. So if you diet, then adding exercise on top of it has a net effect of net benefit of 2 pounds. Okay, so therefore, this is an example of additive effects. The effect of exercise is the same whether one diets or not. Okay, so that's what can be seen in an interaction plot that is showing additive effects. The lines are parallel. Okay, so that's recaps what I just said on the last slide. So the plot suggests that exercise helps you lose 2 units of weight whether you diet or not, and so there's no interaction. Now, this is of course just made up data, and this might not actually be realistic. So for example, what would the plot look like if exercise is actually more beneficial when dieting? Okay, so if exercise is more beneficial, so if exercise helps you, has a net effect that is even larger when combined with dieting, then there would be an example of an interaction. So it might look like this. So if exercise is more beneficial when dieting, then the corresponding plot, when these 4 treatments are put together in this way, you see now that when there is dieting, then the difference between exercise and no exercise is larger. So here it's set to be about 3.5 units. Okay, so exercise helps you lose 2 units when not dieting and 3.5 when you are dieting. And so visually what that looks like is the lines are not parallel. Okay, so that's what we're looking for in these kinds of plots. When the lines are parallel, that suggests we have additive effects. When the lines are not parallel, then we can say, at least visually speaking, it looks like the factors would interact. Now, one thing, of course, to be careful of is we haven't shown how much variability there is around these means. So the box plots, if we overlaid the box plots, might actually be quite large, but that would come out when we actually do hypothesis testing. This is just a visual to help us assess whether there's interaction or not. Okay, so here's another example. So suppose you need to cram for a final exam, or you should cram for a final exam. It's the night before, and you're deciding whether you're going to stream some more Netflix or do some cramming. And so let's just, for simplicity, say you either do or do not for each of these factors. And so if we conceptualize and suppose that, okay, if we cram, that helps, and if you relax a little bit, that also helps, but you don't have enough time. The key thing, you don't have enough time to do both, and so we know that if you stay up all night, you probably cannot do math, and so you would actually do worse. So what would the interaction plot look like? Well, here is a hypothetical example. So suppose we could carry out an experiment like this. So if our guesses were right, then this might be what the interaction plot looks like. Okay, so so on the x-axis, I put whether we do last-minute studying or not. So if you're not watching Netflix, last-minute studying helps you do maybe about 30 points better. Oh, I just realized that these averages for the grade are not realistic at all, but that's just ignore that for now. And likewise, okay, so if you do Netflix, then that so when you don't study, then that also improves your score a little bit, but not as much as if you were to do last-minute studying. Okay, so so last-minute studying, no Netflix, moves you from about 30 to like a 60, and then if you just watch Netflix and don't study, then that would move you, say, to about 50. Now, what we said earlier, if you do both, you actually do worse. Then that's why we see in this case it's actually possible for these the lines on the interaction plot to actually intersect. Okay, it doesn't need to intersect to have interaction, but it's possible that there's such a negative effect that the line can actually intersect. So that's why we see in this bottom right red point, that's where you do both, and you actually do worse. You do worse than if you were to just either study or do Netflix. Okay, so that's this bottom right point. Okay, so just to give you some further visual examples, so if you look at different interaction plots, you should be able to identify which ones have interaction. Okay, so remember we're looking for parallel lines. So this one on the top right does not have interaction. So here in this top right panel, the two factors have additive effects. Okay, whereas for the other three, we see different types of interaction. Okay, so here we have a very negative effect once you do both. Okay, so here is a somewhat milder effect. Now on the bottom right, it's possible that one factor might not actually kick in or have any effect until you combine it with the other. Okay, so we see that this red line actually does not have an effect until you actually combine it with the other factor. Okay, so I'll leave it to you to think about what might be some possible examples of that in a practical context, and I'll come back and tell you a little bit more about that next time. Okay, suffice for now, just make sure you know how to look at these plots and be able to identify when it looks like, at least visually, that there is interaction. Okay, so that was just 2x2 case. Of course, you can take more levels of A and B. So here we notice there are now 6 treatments. Okay, so two levels of A and 3 levels of the other. Okay, so again, we're looking for a similar thing. So in this left panel, there is no interaction. The effects are additive because the difference between yes and no for this between these two lines is the same no matter which level of the x-axis you're using. You see the difference between the red and the blue is the same for each of these levels. Okay, so therefore it's an additive effect, no interaction. Whereas on the right panel there is interaction. The effect of changing from yes to no for this factor on the y-axis varies a lot depending on what level of the factor on the x-axis we're in. Okay, so suffice for now, we should be able to identify visually whether there is interaction looking at these plots. Okay, so just to remind you, these are just visuals. Okay, so to actually test whether they're significant, we need to do hypothesis testing. And I've already gone through this third point. So when there's actually just 2 factors and 2 levels, there's only one unique interaction, and that can be done using a test of contrast. Okay, when there are more than 2 levels, then we need to do ANOVA. And so what's going to determine whether the ANOVA F test is significant or not is, of course, the variability among the treatment means, which is not shown in these plots. Okay, so that's the size of sigma squared. Okay, so how much residual variability is going to affect whether the interactions that we identify visually are actually statistically significant or not. Okay, so that's those are the slides. And if you wanted to draw these interaction plots in R, you can feel free to make use of this code, which you can use in R to make the plots I just showed you with the red and blue color coding. Okay, well, we are going to come back later for the rest of the slides, but first we need to do two things. So first we need our musical break, and then I need to do show you the rest of the equations for doing the hypothesis testing. Okay, so looking at the list of requests, today I'm going to do the second Scherzo by Chopin. So I'm going to move this over, and we'll start that in just a moment. Okay, so now we need to do hypothesis testing. So I guess we have one lecture after. So currently on my list, I will do Claire de Lune and probably one other piece on Wednesday. Okay, so in order to do our hypothesis testing for interaction, we need to do a quick sum of squares decomposition and then come up with the corresponding ANOVA table so that will allow us to carry out the test of hypothesis for whether the interactions, there were any significant interactions. Okay, so let's start again with sum of squares decomposition that we already have seen, and let's extend it to make it work for this case. Okay, so let's start with the residual sum of squares. So from the last thing I just erased over there, we know the residual sum of squares is expressed, can be written this way, so yijk. So the square differences between each observation and the treatment mean. So treatment mean, so factor combinations I and j. Okay, so all the replicates assigned to that treatment. So we already know that's the residual sum of squares. We also know that's the treatment sum of squares. Okay, so again, it just looks a little bit different, but it's the same treatment sum of squares we saw in the case of a completely randomized design. So treatment sum of squares. Okay, so that's why summation over the ijk. Okay, so treatment sum of squares is the difference between each treatment mean. So now the treatment means are represented y bar ij dot from the overall mean. And so we can write it equivalently by doing the third summation. So we can sum over the same thing for over the replicate. So there's r of them. So this is equivalent to just writing it as r times summation ij of the treatment means from the overall means. Okay, so what's the key new idea here is, so here's the new idea. So now instead of taking a single sum of squares for treatment, we're now going to break down the sum of squares for the treatment into three subcomponents. Okay, and so from the model, we already know what those three components are that's going to make up the treatment sum of squares. There's the effect of factor A, the effects for factor B, and then the interactions. Okay, so that's where we're going with this. Okay, so decompose treatment sum of squares in terms of A, factor B, and interactions. Okay, so again, remember we already know what the residual sum of squares and treatment sum of squares, so we just now need to figure out how these three components add up together to give us the overall treatment sum of squares. Okay, and the way to do that, fortunately, this is actually quite straightforward because we've already seen how to do the sum of squares decomposition for randomized block design. So all we have to do here is use the SS decomp from our randomized block design. Okay, so let's take this thing on the right. So I'm just going to leave out the r because it's just going to be a constant that's multiplied on it. So what we have here, so this is summation over I and j. Actually, I'll just write it in so then we don't miss it later. Okay, so this starting on this side is the treatment sum of squares. So the treatment means minus overall mean. Okay, so this is the treatment sum of squares. And this decomposes into exactly, so now if you look at the randomized block design, so all we have to do is ignore the fact that there's an R outside, and also ignore the fact that we have a third dot here. Okay, so if you look at that equation, we notice it is exactly the same as this one. Just pretend that there isn't an r and pretend that there's no third subscript. So y bar ij minus y bar dot dot. Okay, so that decomposition actually applies exactly here. All I have to do is add another dot, okay, because we're averaging over a third subscript, and then put an r in front, and then we're done. Okay, so this is what the decomposition looks like. So, so again, I have to carry out the r. Okay, so we have summation. So first one is to do I dot. Okay, so in the RBD we had y bar I dot minus the so the y bar I dot minus the overall mean. So now we just have an extra dot. So we have y bar dot dot dot. Okay, so the second term from the RBD decomposition was the block term, and now it just looks like this. So again, there's an r outside summation. Okay, so in that case, it was just dot j, but I have an extra dot, so carry that through. And the last term was the one that involved the combination of the yij's, and you subtract the block means and the treatment means. So again, just copy that expression down, just put an r in front and an extra dot here. So yij dot minus. So here is where we had I dot, so now we have an extra dot, and then we have dot j, extra dot, and then now we have the overall mean, so there's 3 average over all 3 subscripts. Okay, and so this is mathematically correct. We didn't even have to do any new math for that because we already know this result follows. In fact, so now that we've written down this whole expression, if you just delete the r and you delete the third dot, you'll notice this exactly matches the sum of squares decomposition that we saw for randomized block design. So therefore, this is mathematically correct. So all I have to do here then is just label all I have to do now is label which sum of squares refers to which one. There are 3 sum of squares here, and they correspond to, the sum of squares for factor A, factor B, and the interaction. Okay, so how can we tell which one is which? Okay, so look at what this first one is referring to. Okay, so this is looking at the ith level of factor A. Okay, so these are the difference between the levels of factor A from the overall mean. Okay, so therefore this is the sum of squares associated with factor A. Okay, so we're going to call this one sum of squares for A. Okay, so sum of squares, and I'll subscript that with A. Okay, that measures the effect of the different levels of factor A on the average response. Okay, so likewise, look at the second piece. It looks like we're taking the jth level of factor, taking different levels of factor B, their averages, and comparing them to overall averages. So this is the sum of squares associated with factor B. And so finally, well, by elimination, well, of course, this is the sum of squares associated with the interaction term. And in fact, that should make sense because this thing in here, so this expression, all these 4 summations in here, you notice this looks very much like the estimate for gamma ij. Gamma ij hat looks very much like that. Okay, so not surprising, this is the sum of squares associated with the interaction. Okay, so I'm gonna abbreviate this with SS, and I put an I here to stand for interaction. Okay, and so that's basically all the new theory for the sum of squares decomposition. And so the only thing we now need to do is to put all this stuff inside some ANOVA tables. Okay, so let you get this down first. While I mention that we're going to look at 2 forms of the ANOVA table. So we've seen the form of the ANOVA table when we're dealing with completely randomized design and T separate treatment. So we're going to start with that one, and then we're going to do a second version of the ANOVA table, which breaks down the treatment sum of squares into these 3 quantities. Okay, so now I'm going to clear the board and let's start. So just 2 more ANOVA tables to illustrate this point. Okay, so the first one is the usual ANOVA we've already seen, and it's just worth writing down again because then you can put the two side by side and compare what we use these ANOVAs for. Okay, so ANOVA tables. So there's two of them. Okay, so the first one is the CRD. Okay, so CRD for T treatments. Okay, so right, so let's put in the columns here. So source, sum of squares, degrees of freedom, mean square, and then F. Okay, so this so there are treatments. This has treatments and residuals only. Okay, so this is the same ANOVA table we use to ask whether, so what do we use this ANOVA table to do? We ask whether there are any differences among the treatments. Okay, so we can still do that ANOVA table in this case. So we just have just one row for treatments and one row for residuals. Okay, so I'm not going to write the expressions, but I'm just going to abbreviate that. So this is your treatment sum of squares. Here's your residual sum of squares. Treatment degrees of freedom, that's T1 less than the number of treatments. Residual sum of squares, that's the number of treatments, so TA, TB times 1 less than residuals. Okay, let me put a little more room. So mean square is to divide sum of squares by the degrees of freedom to get your treatment mean square. And then your residual mean square is simply the estimate for sigma squared. So just write this one as usual. Okay, and then the F value is to take the treatment mean square and divide it by our estimate of the residual variance mean squared. Okay, so what do we use this ANOVA for? Well, the key purpose is to ask whether there are any differences among treatments. So, so in particular, this statistic here, this F statistic, is used to answer this question. So we use this to test if there are any differences among the T treatments. Okay, and the reference distribution for that, and compare this one to F distribution. Okay, so we look at this statistic and look up the corresponding quantile for the F distribution. So the degrees of freedom are T minus 1, and then TA, TB minus 1. Okay, so that's our plain ANOVA for asking whether there are any differences among treatments. Okay, so that's the first ANOVA table. So we can still do that. This is the form it would look like in this case. Now, the second ANOVA is to deal with the ANOVA for the interaction model. Okay, so this is the one with vector A, B, and interaction parameters. Okay, so just to emphasize, all this is doing is taking this treatment sum of squares and breaking it down into the three components that we had just talked about on the previous board with the decomposition. Okay, so again, it's still a little more room, so sorry over here. So source. Okay, so now the source breaks down treatment into the three components. So we have A, B, and interaction, and then residuals. Okay, so these three. So you just highlight here. So these three correspond to the treatments. Okay, so the sum of these three sum of squares add up to your treatment sum of squares. Okay, so sum of squares, again, I'll just write the abbreviations. We have sum of squares A, sum of squares B, and sum of squares interaction. And so these three add up to the treatment sum of squares. Residual is the same thing. You just copy that down. That doesn't change. Okay, and then the degrees of freedom associated with it. Just make it a little clearer. Okay, so degrees of freedom. So this is counting how many free parameters. So for A, we had T sub A minus 1, free parameters, and then T sub B minus 1. For the interaction, we found a couple of boards ago, so it was TA is the product of those, TA minus 1 times TB minus 1. That's why if there's only 2 levels for each of them, then there's only one interaction. Okay, so that's where we see the same idea again. Okay, and then the residual line is exactly the same, so just copy that down. That is TA TB R minus 1. Okay, so now we can again calculate the mean squares by taking the sum of squares and dividing by the degrees of freedom. So you have your mean square associated with A, factor A, mean square associated with factor B, the mean square associated with interaction, and then the mean square residual is again the same sigma squared hat. Okay, so now the only difference here now is you notice there are 3 different F statistics that we can now calculate. All right, so you can take each of these mean squares and divide by sigma squared hat, and that would give us a possible F statistic. Okay, so we can calculate an F statistic for testing the effect of factor A, so that'd be mean square A divided by sigma squared hat. We can do the same for B. So we take the B's mean square and divide that by sigma squared hat. And finally, the one that we're most concerned or interested in for our purposes right now is to ask whether there is significant interaction. Okay, so therefore, not surprisingly, the F statistic associated with the interaction is the key one that we're going to use to test the hypothesis for whether there is any interaction. So that's the mean square interaction divided by sigma square. Okay, so this one is the key statistic for that purpose. And so let's just complete this. So you can also write down the total. So you have your total sum of squares. So that adds up to the total sum of squares, and degrees of freedom add up to the one less than the sample size. So that would be number of treatments, so TA TB times number of replicates. So that's the total sample size. Then minus 1 is, as usual, the degrees of freedom for the total. Okay, so let's just point out what we use these different F statistics for. Okay, so with this guy, so let's start with this guy. So this is the one that we're gonna key in on today. So we use this one to test whether there are any significant interactions. So this tests if A and B interact, if any interaction. Okay, so this is so the null hypothesis would be that all the interaction parameters is 0. Okay, so that's what this F statistic tests. Okay, and so we would compare that to the corresponding F distribution. And so how you read off the degrees of freedom? Well, the numerator degrees of freedom is the one associated with that row in the ANOVA table. Okay, so this is done using the F test, and the distribution that we're going to look up is degrees of freedom for the interaction, so TA minus 1, TB minus 1, and then the degrees of freedom for the residual, TA and TB R minus 1. Okay, so that would be the correct F distribution that we would use, and we would carry out this ANOVA test in exactly the same way. Okay, so that's how we test for interaction. And so if the interaction is not significant, then that tells us that we can model the data well enough just by using additive effects. Okay, so that's how we link everything we've been talking about together and test formally for whether the interaction is significant. Just as a side note, you can also use this table to test. So if you throw away, if there's no interaction, then you can also then ask whether the main effects of factor A and B are significant or not by using the corresponding F statistic and also the corresponding F distribution. So you can also use this test for the effects of A and B, though for now let's just focus on the interaction part. Okay, so that's basically the conclusion here. And so so this is just to wrap this point up. So if interaction is not significant, then that means this null hypothesis is plausible, and so we can just use an additive model. Then that means it's plausible for the interaction parameters to be 0, and we can reduce the model, throw away the interaction, and just model it as additive effects. Can reduce the model with additive effects, which, as we talked about, has fewer parameters. It's a simpler model, and if the simpler model can explain your data well enough, then we don't need to use interactions. Okay, so that's the point. We can reduce to model with additive effects. Okay, so let me just see if there's any questions in chat. I think we're okay. So I will let me move back to the slides and wrap this up. Okay, so we are now back in our lumber lab, and so this picture is just proof that we actually do these experiments in an industrial lab. So that's part of our team at UBC, where we carried out some of these experiments. So let's assume for this purpose that we're going to do a different version of the experiment, a much larger one. Okay, so we're going to set this up by buying up a bundle of 300 pieces from Home Depot. So let's pick the middle grade, SPF number 2. So we have 300 pieces of 2x4s. And we're going to stress the pieces at 5 different load levels for 1 month. So study effects of pre-stress. So load levels ranging from 0 to 4,000. And so this time we're also going to compare 2 different tests, so bending and tension. Okay, so we think of this as a 2-factor experiment. There are 5 pre-stress levels, and then 2 ways of measuring the strength. So we'll treat these as our 2 different factors. And so we can only, as you saw in the video, you can only take 1 test, and then that's going to break the piece. You cannot load it into another machine and do a second test. Okay, so we can only get 1 measurement per piece, so that's why this is a 2-factor experiment, so 10 treatments. Okay, so you can look at this video later if you want to see what the tension test looks like. It basically pulls the piece apart until it breaks. Okay, so here's the setup. We have 2 factors. The first is load level, second is test type. 5 load levels, 2 tests, so 10 treatments. 300 total, so we have 300 pieces to work with, so we're going to randomly assign 30 to each treatment. And the question is, well, is there any differences among these treatments? And specifically, also, is there any interaction between the 2 factors? So in this practical case, asking whether there is interaction is asking whether the pre-stress at these load levels have the same effect on both bending and tension. If they do, then we simply can add up the 2 effects, the effect of the load level and the effect of the test type. Otherwise, we need to have interaction. So maybe the stress does more harm for, say, tension than bending. So then the 2 factors would interact. If they do not interact, then the effect of the load level would be the same no matter which test we're using. Okay, so that's what we mean by interaction in this practical case. All right, so we can pull up the file. It's called Lumber two-factor, and we can work with this data. So here are the summary statistics. 30 replicates for each treatment. So we see indeed the strength of the wood goes down with a stronger pre-stress level, okay, and for both bending and tension. Okay, and so the way to visualize that is an interaction plot, which we talked about earlier today. So here there are 10 treatments. Okay, so I've used the black line to represent bending strength over the 5 different load levels, and then superimposed is the corresponding line that maps out the averages under tension. Okay, so visually, how do we know there's interaction? Well, we look for whether the 2 lines are parallel or not. And so if they're relatively parallel, then we might, at least visually, would look like there would be no interaction. In this case, it's not quite parallel. It looks like the bending strength does decrease a little bit faster than tension as you go from low pre-stress to high pre-stress. So it looks like the gap between the 2 lines is shrinking a little bit as you move from left to right. So the question is, well, is that actually statistically significant? Okay, so that's where we need to do our test for interaction. Okay, so I'm going to go over to RStudio and show you. Okay, so I'm going to load up this data. Okay, so first thing I want to point out with R is now, okay, so if you look at the data, you notice there is now the 2 factors, right? So you see there's the test, there's which load level is applied, and also the strength value. Okay, so remember the treatment is really a combination of both test and load, so we need to combine these 2 columns to generate our 10 unique treatments. Okay, so to do that, we can use the colon command, the colon operator in R. So this basically joins together the test column and the load column. So it constructs basically a concatenated column, and so it's now going to have 10 different unique values for 5 times 2, 2 tests times 5 loads. Okay, so then there's now 10 different groups according to that have a unique value of test and load combination, and then I'm going to calculate the mean using tapply. Now if you do that, it's going to give an error. Okay, it'll say that blah blah blah, the arguments must have the same length, etc. And so the reason for that is because R is treating load as simply is treating it as a number. Okay, whereas we want to treat load as different levels. Okay, so in R terms, it means it's treating it as numeric when we want it to be a factor. Okay, so test is okay because it's just a word, bending and tension. So R knows that there are 2 factor levels here. But for load, R thinks it's just a number going from 0 to 4,000. So the way to address that is simply to put this as dot factor to wrap around the factor that R is reading as a number. And so we do as dot factor, and so now this works, and this gives us the 10 treatment means which we saw on that last slide. Okay, so that's the point that's talked about on here. So this is exactly what I just walked you through. And so the last part is second part here is simply to so this calculates the treatment means, and this reformats it into a matrix. Okay, so this has the 5 by 2 table that I showed you earlier. First row is bending, and then the second row is tension. Okay, and then with the data structured in this way, I could do a different version of the interaction plot. So this is not quite as fancy as the other one, but it conveys the same message. So this is the plot you saw on the slide, where I'm using red and the black line to represent tension and bending, and that shows the averages in each treatment group. So that's done using the matplot command in R. Okay, so the last part is simply to look at the different ANOVA tables that we can compute. Okay, so I'm going to use the slide to show you those aspects. Okay, so first, just to recap, we have degrees of freedom, and so you can compute these quite straightforward using the formulas on the board. So treatments, so there are 10 treatments, so 9 degrees of freedom, and then for loads, there's 5 loads, so 4 degrees of freedom. For tests, there's 2 tests, so 1 degree of freedom. And so now from there, you can get the interaction, number of free parameters in the action. So TA minus 1, TB minus 1 is 4 times 1, so there's 4. And that makes sense because the 9 degrees of freedom has to break down into the 3 subcomponents, 4 plus 1 plus 4. Okay, so we're going to do the ANOVA, and so the final 3 commands to show you the different ANOVA tables. So the first ANOVA table here is to simply treat it as 10 separate treatments. Okay, and in other words, this is basically asking R to estimate a tau I for each of the 10 separate treatments. So the way to carry that out is to again use the colon operator to join the load and the load factor and the test factor, so that R sees it as 10 treatment combinations. And so this is the ANOVA table that allows us to test whether there are any differences among the 10 treatments. So that's why you see there are 9 degrees of freedom here. Okay, so indeed the F-test is extremely significant, very, very small. So there are indeed significant differences among the 10 treatment means. Okay, so that's the ANOVA table number 1 on the board, which so this is how we should start, is to ask whether there are any differences at all among the treatments, and in this case there are. So the follow-up question would be to ask whether there is a significant interaction, now that we know that there are differences among treatments. So now this second slide is the ANOVA table number 2. It decomposes the treatment sum of squares into the 3 components. Okay, so the way to do that is replace the colon here by the asterisk, and so that tells R to actually break down into the effect of A, the effect of B, and then the interaction. Okay, so you can read off from these lines here which is which. Okay, so this is that $ load. So this is the effect of load, and then the second row is the effect of test. Okay, so this is the sum of squares for the load, sum of squares for the test, and then finally the third row where you see the colon again is where R represents the sum of squares interaction. Okay, so this part is the interaction. So you can easily verify that these 3 sum of squares adds up to the treatment sum of squares that we saw on the last slide. It decomposes both the degrees of freedom and the sum of squares. Okay, so as pointed out on the board, we can now calculate 3 corresponding F statistics for these 3 rows. So it's taking the mean square in each case and dividing it by the residual mean square. Okay, so we have 3 F statistics. The one that I'm going to focus on is the interaction F test. So the interaction F value is 1.84. Okay, and so R calculates the p-value to be 0.12, so in other words, not significant at the 5% level. Okay, so what's the F distribution that R used to get the p-value? Well, you can just read it off the table. It's an F with 4 degrees of freedom in the numerator and 290 in the denominator, and that's what this value of F was compared to get this p-value. Okay, so in this case, we see the interaction is not significant, so it's also possible to recompute the ANOVA table by taking out the interaction row, and so that's this last ANOVA table here. So here, in order to get R to drop that row, instead of the asterisk, we just replace it back with the plus sign. So you're just basically taking the additive model of factor A and factor B, and then asking R to compute the ANOVA for that. And so you see the resulting table, it basically just drops out the interaction. So you now just have the effect of load and the effect of the test. And in fact, if you pay close attention, this ANOVA command is exactly the same ANOVA command that we used for randomized block design. Okay, so in RBDs, we also had the same syntax. We would take the treatment and then we plus the blocks. Okay, and so we had a treatment effect and a block effect, except now we have a factor A effect and a factor B effect. And so as far as R is concerned, it is blind to what these things actually are. You could plug in treatments and blocks, or you could plug in factor A and factor B. Well, mathematically, it's doing exactly the same thing. The decomposition works exactly the same way. So R does not know whether you're plugging in a factor and a block, or a treatment and a block, or two factors. There's no mathematical difference. Okay, and so that's why, just to make a note of that, this is conveyed quite nicely by this meme that, in fact, mathematically there are no differences between blocks and factors. It's really how we interpret them. Okay, and so that's the point I'm trying to get at here on this slide. Okay, so what does this mean? That instead of treatments and blocks, we now have factor A and factor B, and so we care about, of course, that both of them are indeed significant, and that we can add together the effects of factor A and factor B to explain the observed data in this model. Okay, so I think that covers everything I wanted to say for this case. So before I sign off, I'm just going to go back to the computer to check if there were any questions. Okay, so there is one question. It says in 2x2 case, we can use the t-test to test for interaction. So what is degrees of freedom for the t-test? So the degrees of freedom, okay. So you're only testing for there's only one unique interaction. So there's only one degree of freedom in the interaction. But what's the degree of freedom we actually use in the t-test? Well, it would be the degree of freedom in the residual. So there's no change there. So we always use the sigma squared from the ANOVA table to carry out contrast t-tests. And then the correct t-distribution to look up would be the degrees of freedom associated with that sigma squared. Okay, so I think that answers everything. So again, if you enjoyed today's video, make sure you like and subscribe, and we'll come back for our final lecture on Wednesday.